Ben Holmgren and Ryan Hansen's programming assignment 4. I'm Ben Holmgren. I'm going to be doing the demo since I've got the better setup for it. So to start out, we'll show off that we've implemented successfully this nice pretty print, and that indeed we actually are creating routing tables and changing the router constructor given to us. So to start out, I guess we can just observe how we're going about implementing this routing table. We've got a dictionary for each router, so this one corresponds to router A, and this one to router B. And all that's going on is we are just keeping track of the distances to the nodes that we know in the dictionary. And if we don't know a node, we just give it some huge distance value, and then we can update it later. So I guess to demo this, how is this working? Well, we start out, and indeed we do have a really nice implementation of the pretty print. And we're getting what we should expect. So we're getting that we don't know for router A, we don't know anything about router B, and we don't know how to get to this host 2 quite yet, because you'll recall from the topology that router B is between router A and host 2. And similarly, kind of the opposite is true for router B, where we don't know how to get to host 1 and we know nothing about router A. And so now, moving on to step 2, our goal is to send route updates and do it correctly. And the way that we're going to do this is we're just going to broadcast an update from this router A first and foremost. And what we should find is that, so effectively we're sending the information from router A to router B, and router B can then update its information. So router B can say, oh, this is the distance if I go through router A to get to host 1. That's shorter than the distance I was initialized with, which was this huge value that's just a class variable that we set. And using these updates, if we can pick a node that's, if we can go through, say, router A to get to host 1, and it'll be faster than what we've been able to do before, then we just update that value. And we also update this row for router A, though we don't know everything yet, right? Because router A doesn't yet know how hard it is to get to H2. So now that we've gotten this update, we're going to broadcast it to all of our neighbors of router B, which means that we should be able to update router A, which indeed we can do now. So router A not only has all of the information from router B, which is correctly computed, but also can correctly compute its own information in row A, for router A in that first row. So now router A has a complete routing table using this Bellman-Ford process of just finding the shortest path from nodes. And then, yeah, so let's see. So now router B shouldn't have all the information yet, though. So now we have to rebroadcast router A to all of its neighbors so that router B can have the full routing table. And indeed, we get the full routing table from router B. And finally, we allow our system to converge, and here are our 2 converged routing tables, which, if we look back at the prompt, should be correct. So yeah, I believe that covers all 3 of the steps for this first part of the problem. We print things out nicely, we implement a dictionary for our routing tables, we correctly send route updates, and we use this shortest path Bellman-Ford equation just to update our routes as updates come.